Alright, this is video number 3. Video number 3 will be exceptionally longer since it will cover the big collision changes that were done this quarter. The very first thing that I'll show off is a brief demonstration of the entire thing working together all at once. So we start off with an AABB of our soldier right here. We have an AABB for our tank. Our user-defined volume for our soldier is an AABB, and for the tank it is an OOBB, as you can see here. So going briefly into this, these macros are just so I can turn on and off the visualizer without having to comment things in and out, or I can see just certain ones. I use this for debugging, but this can be removed later on if need be. But moving on, here in the game, I have my GAM. In the bottom you can see our terrain. I'll show that off a little bit later, but our terrain highlights where our soldier would be touching the ground. But you can also see that we're also not touching these two AABBs. So what I'll do is I'll collide right here, and I'll move the GAM so we can prove that they are indeed colliding. So as we can see, these two are colliding. So the next thing that we do is we take our B-sphere and we check our B-sphere against our group's AABB. I'll move a little bit more forward. So now you can see that we've changed our B-sphere here to orange, and now we will check the B-sphere of our player character right here against this other B-sphere that we've already know is a collision pair. Oops. So I'll move it in. And now you can see that that one has changed yellow. So we're moving down into all of these collision tests. So the very last one is just the collision against the personal volume, which is this bottom half's OBB against the AABB of my soldier. And the AABB covers the same red square that the group has, since there's only one object in the group. So just keep that in mind for the reference. I'll move the GAM a little bit closer so you can see the final collision test. So I'll move in my soldier. So nothing, 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 and we touch, and then we enter our tank. Once we enter our tank, we're able to control it as we want. I can also exit the tank. So in this case, I've exited and I enter over there. And now I'm able to show the collision against right here, my terrain. So I cover 4 blocks of this terrain. The first 2 are not touching, and the second 2, again, since it's just an approximation, I am touching these 2 ABBs right here, or as close as I would be, thanks to round off errors. But as I move off, I'm not touching these 2 blocks. This would be much more refined the closer that I get to a high-res model. But for general collision testing, it's pretty accurate. So that should cover that part. Moving on into the actual diagrams. Here I have the diagram, and I'll start off with the collision volumes. All our collision volumes derive from collision volume. We have a separated type for our B-sphere, since all collisions will start off with a B-sphere type collision, and moving further on into that, we have this virtual class of our volume bounding boxes. So all our bounding boxes have a local max and min point and world that we need in order to do the proper calculations in our math tools. But we also have accessors for those parameters. Further on into, we have these 2. Also to mention, these are protected, as they show down here. because we want the children to be able to access these variables without having to go through the accessors. The accessors are for things that aren't the children. These are private to our AABB, but it has its appropriate accessors. And as I mentioned, our AABB needs our world, min, and max point. It is possible to do it through here, but if we're updating our data whenever an update happens, we'll get this information virtually for free. So this information is here. Moving further along, I'll illustrate our collidable, and we have our 3 collidables, our B-sphere, an ABB, and an OBB. I think that was relatively clear. We have our collidable registrations and deregistrations with their proper thing. We have our collision callback there, our terrain collision callback, which is when a terrain has been placed into the screen. We can get our collision volumes. We try to keep const correctness, so when we're getting a collision volume, we make sure we don't mess with it. We have our set collider model. By default, we set it to a B-sphere if the user doesn't explicitly state what they want. We also have our update collision data, this one, which if the user wants, if the user provides the scale factor along the X, Y, and Z and it's equal scaling, it's much faster that they just pass it through. So I left this function from last quarter, as I mentioned to you before. But we also have the regular matrix math, which we do a little bit more extra work just in case the user doesn't know, or we do weird scaling things. Granted, for collision, we don't want to, but we can extract the scale using this second part. As you wanted to know, we don't own any graphics objects. We merely have pointers to our model and our volumes. The only thing that a collidable owns, in theory, is this upper half of stuff. And really the only thing it does is the current state. So our main methods, I've already shown the update calls, I've shown the accessors and initialization, but I'll go into the other ones very quickly. So we have our same thing, our overloaded compute data, which is special for our B-spheres. We have our get center and get radius, which are special to our B-spheres. We have our intersect with other, which is the beginning of our double dispatch. We have our intersect with a B-sphere, with an ABB and an OBB, and that's after the double dispatch has been resolved. These calls will be made, and the proper intersection calls will be done. We have our calls right here. So our B-sphere collision test, which goes into calculations, etc. So our compute data is right here, and as I mentioned before, we can get the scale from the world matrix, but that's a little extra work. So when possible, we can minimize basically tearing apart that world matrix by just giving in the scale value. Again, it's not that big a deal, but I thought it's a little bit more helpful, so that way the user is responsible, and this also kind of guarantees that the user will always give a perfect X, Y, and Z scaling. Uniform scaling. Again, further going into the collision volume, the thing that I mentioned about the our bounding box volumes, this is used both by our ABB and our OBB. We have a protected world, min and max point, protected because we want both of our derived classes, that being our OBB and our ABB, to be able to access those values without having to go through pesky accessors. We can have our compute data, again, in much of the same way as everything else. We also have our debug, our intersects. In our AABB, we have the same thing. Everything is here, but the only difference is that we have a world min and max point that is special to our ABBs for calculation. We have our proper accessors. We have const correctness whenever possible, so that way these values aren't modified. But going further along, we'll go into the collidable groups. The collidable groups are right here. And we have our, I'll start off with the public API. We register collidable groups in our scene, initialize. We can get our collections, which are done through each one of the pair, self, and terrain test commands. This will return a constant reference, so that way we're not passing around, we're not copying data as much in many different places. And we do have a deregister command for when we want to remove something. We have an update that's called once per frame. When everything is done and executed, I'll show off what that does. We have our get groups AABB, which where we get the groups AABB, and that's done for our collision test. And we have our reset AABB. This is something that I use because I just wanted to make sure that our AABB wasn't going to be visible on screen, or it would be in an arbitrary place that doesn't matter. Further on, we're able to delete things when our collidable group becomes destroyed, so that way we clear out as much memory as possible. Going further on, this is an instance. We have a quick remove that the collidable group holds on to, so that way it knows what it can remove when a pointer is passed in. So we can quick remove it from our list. And if our list is 0, we clear out our list, and we clear out our quick remove since there's nothing in there. This just ensures that we're clean, and we set our min and max points to this really far off value that doesn't matter. This generally doesn't matter, but I like to make sure that on the next update, my min and max points will be updated to something reasonable. So going into the private update, we have our, we iterate through our collection of our collectibles. And the sad part is we have to check if any one of those objects have moved. Because there is a possibility that one or multiple things could have moved on screen. So what we do is we get the B-sphere. From the B-sphere of each one of our objects, we get the min and max points from those B-spheres. And what we end up doing is for everything in our group all the way until the end, we do the same thing, but all we're doing is we're comparing our min and max point to the next one. So we always make sure that our min and max point will cover the extent of our list. And like I said, we do this with our first object, and we compare that that first min and max point with every other min and max point. So that way, at the end, we'll have our min and our max point be the min and max point through all the bodies in the array, or sorry, in the list of our collidable group. Very last thing, we return our collidable group back to our pair command, so that way we're not passing around that much data, we're just passing around constant references. Going into the collision manager, we have our registrations for self, collision terrain. We have the ability to remove them, so that way we can not test them whenever needed. to process our elements, we execute each one of those base commands, and we either enter our pair registration, our self, or our terrain. I've shown off the pair. The self is the same. The terrain is very different, and that is because collisions against terrain require us to iterate through our iterate through an area based on our min and max point of our collision volume. So right here we get our volume, which is this. So since we have our AABB of our collision volume, sorry, not of our collision volume, but of our object within the collision volume, because we want to make sure that that a collision happens between any of those objects. We get our min, our position, and our radius. From that, we have our AABB. We can get our min and max points from those values. And since we have that AABB, we can check, we can query for a list of candidate cells. Going briefly into this, what we do is we ask for what terrain we're currently using. I have this call within terrain, which gets the cell below, so we can get the self on our min point and our max point. Our min vertical is the minimum vertical value. Oh, sorry, I should probably go into what a cell height width is. Going into a cell height width, when we get the one cell below, we return a struct of data that gives us our position of the cell horizontally, vertically, and the exact number of that cell. So we check our minimums vertically, our maximums vertically and horizontally, and at the end we have our minimum vertical, which will be the top left corner, and our max and max being our bottom right corner on the terrain. And through that, we can calculate our start cell and our end cell. And iterating through that is very simple. We take our start cell and we go across, and when we reach the point where we've passed our max length, so basically our width, we go down, one. We reset our vertical back to the minimum value, and we move on to the second row. So we basically go 1, 2, 3, 4. I've reached the end, down to 5, 6, 7, 8. Granted, these numbers are actually calculated, so they're calculated so we know those numbers because it's arbitrary depending on the size of our ABB and the number of cells. We have our iterator equals test and not equals test to make sure, and we're able to get our min and max point from the iterator because we know the current cell that we're currently on. So back to this, we get our begin. So after we've queried, we get the begin cell, and we get our end cell, and we iterate through them as I mentioned. So we get the first one, the second one, we get our min and max, and from that we do our test. So the very first test that we do is we check the B-sphere of our object against the AABB, each AABB of these cells. If they're not touching the ground, we just leave a default color. If they are touching, or they have the probability to touch, we do a much more advanced test, which is our collision volume being whatever it was. So in our soldier's case, it's the AABB, and we do our ABB collision against the ABB of our current cell. And if that collides, then we're able to call terrain collision. If that doesn't happen, we give it this extra color. So we try and early out as much as possible by not touching the ground. And if we are, then we are touching the ground. We call this one. If we're almost there, we just set the color. And at the very end, we call our visualizer to render that given cell. Going into our visualizer will be what I do next in the next video. I think I have covered everything except for the math tools, but that will be another video later on. So I think I've covered everything for collision. I may have said a few things incorrectly, so I'll just do once more very quickly. Collision volume, 2 derived, this derives 2 more. These are privated because both of these use that information. This is here, so I can simplify data. For compute data, I have 2 types of calls, just in case the user wants to give the full matrix, or a matrix that that also gives in a float being the scale factor, so that way we minimize deconstructing a matrix. We have our proper accessors. We attempt to do const correctness. Whoops, not there. We attempt to do const correctness wherever possible. Right here you can see I call const whenever possible for each one of these things. Our groups, A, B, Bs, we get our min and our max point. We use the first one as a reference. From there, we check all of our other ones because there is the possibility that any of them could have moved. And we get our min and our max from the first one being the reference, and then against every other one. So that keeps updating. So we always have a minimum, we always have a maximum. We set our groups A, B, B. We have our clears and everything else. Our pair test does early pruning, and our terrain test also attempts to do early pruning using the iterator. The iterator basically takes first and last positions given our min and max points, iterates through them first vertically, then horizontally down until it reaches the last cell. And again, we try and prune early before doing our expensive test. That should cover everything. Moving on to the next video.